A pinhole camera is a simple camera without a lens and with a single small aperture. Light rays pass through the aperture and project an inverted image on the opposite side of the camera. Think of the virtual image plane as being in front of the camera and containing the upright image of the scene. The focal length is defined as the distance between the aperture and the image plane where the inverted image is formed. The virtual plane is located at the same distance from the aperture as the image plane, equal to the focal length, but positioned in front of the camera. In computer vision, it is common to use the central perspective imaging model, shown in figure. Consider a three-dimensional point, capital P, with coordinates x, y, and z in the camera coordinate frame. The image plane is located at a distance f, called the focal length, along the optical axis. A ray from capital P passes through the camera center and intersects the image plane at lowercase p, the projected point. Using similar triangles, we derive the projection equations. In the x-z plane, the ratio of capital X to lowercase x equals z over f. Solving for x, we obtain x equals f times capital X divided by z. Similarly, in the y-z plane we obtain y equals f times capital Y divided by z. The image plane is a W by H grid of light-sensitive elements that correspond directly to the picture elements, or pixels, in the image as shown in the figure. We need to convert the coordinates of the projected point P of x and y, computed in meters relative to the image plane origin, which is assumed to be located at the center of the image plane, into pixel units. In addition, the pixel coordinate system has a different origin. By convention, this origin is located at the top left corner of the image plane. Thus, we scale the point from meters to pixels and shift the origin to the top left corner. The pixel coordinates, u and v, are related to the image plane coordinates, x and y, as follows. U equals u sub 0 plus x over s sub x, and v equals v sub 0 plus y over s sub y. Here, s sub x and s sub y are the width and height of each pixel, respectively, because the pixels are not necessarily square. The point u sub 0, v sub 0 represents the principal point, the pixel coordinates of the point where the optical axis intersects the image plane, measured with respect to the origin of the UV coordinate frame. First, we use the previously derived equations that relate the pixel coordinates u and v to the image plane coordinates x and y. We then express these equations in matrix form. Next, we convert them into homogeneous coordinates by adding a 1 as the third component of each vector, allowing us to incorporate translation. Finally, we multiply both sides of the equation by z. We scale the pixel coordinates by the depth z to represent them in homogeneous form. We define the homogeneous pixel coordinates as u tilde equals z times u, v tilde equals z times v, and w tilde equals z. Using the familiar pinhole projection equations, we substitute the image coordinates and rewrite the projection as a matrix multiplication involving the coordinates of the point with respect to the camera frame. The 3D point P is represented as a homogeneous vector. We can split the 3x4 matrix into two parts. The matrix pi is the projection matrix that maps three-dimensional points to the two-dimensional image plane. The product of the first two terms forms the 3x3 camera intrinsic matrix, K, which describes how coordinates on the image plane are converted into pixel coordinates. We want to find the projection of a world point, P, onto the image plane. Here, P sub W denotes the point in world coordinates. P sub C denotes the same point expressed in the camera coordinate frame. Our sub WC is the rotation matrix that describes the orientation of the camera with respect to the world. And T sub WC is the translation vector that represents the position of the camera in the world coordinate system. Initially, the relationship between a point in the world and the same point in the camera frame is described by the first equation. Next, the equation is expressed in homogeneous coordinates, which allows both rotation and translation to be represented within a single transformation matrix. Here, the coordinates of point P are given in the world coordinate system. To convert from world coordinates back to camera coordinates, we use the inverse of the transformation matrix. Finally, the last equation shows how the point P, with camera coordinates x, y, z, is computed from its world coordinates UVW. To obtain the complete projection equation, We substitute the coordinates of point P expressed in the camera coordinate frame. The equation combines both the intrinsic parameters, denoted by K, and the extrinsic parameters of the camera. The extrinsic transformation converts the point from the world coordinate system into the camera coordinate system. Finally, the pixel coordinates are obtained by normalizing the homogeneous coordinates of the projected point. We do this by dividing by the third coordinate, W tilde, which represents Z, the depth of point P with respect to the camera. Click the link in the description to open the Colab demo. It demonstrates the projection of a world point onto the image plane, according to the Pinhole camera model, and includes a derivation from scratch together with an implementation using Corke's machine vision toolbox.